Hello everyone, I am Himanshu Mishra and today we will solve few problems which are related to virtual work and energy principle. So until now we have solved the problem by using the force equilibrium and moment equilibrium methods. So there we have to make the free body diagram and disassemble each member of the free body diagram, use the force and moment equilibrium equation on each of the member, and then we need to calculate the unknown force. We need to solve for the unknown force or the reaction forces. So until now in every topic we have discussed like trusses, beams, we have used the same principle, but today in the lecture we will solve questions which are based on the virtual work and the energy principle. So just to recap, we all know what is work done. So for example, let's say there is a block. So I'm giving the standard example which you might have seen several times in the book. So let's say this is my block, some block A, and I am actually exerting a force F in the horizontal direction, and due to this force there is a displacement in the block. So let's say this is my position S1, and now the center of the block moves to position S2, and the difference is, or the displacement is ds. So when I exert a force F, there is a displacement of a block from S1 to S2 along in the force direction. So it will impart some work. So here the work done is given by force vector as well as the displacement vector. Okay, so work done is a scalar product and it is given mathematically, it is given as a dot product of force and the displacement. So if the displacement is in the normal direction, the dot product means that if the displacement in the normal direction, for example, if the displacement is, this is S1, and if it is displaced to S3, somehow by exerting the same force F, then there will be no work done because this dot product will be zero. Okay, so there will be a work done by a force, so such that the displacement is along the direction of the force. So in that case there will be a work done due to that force. Now in virtual work what we do that we actually exert or we actually impart some virtual displacement in the given system. So these are the displacement which are assumed displacement. These are actually not actually going to happen, but these are actually a assumed displacement. So these are the virtual displacement and we need to calculate the work done by these virtual displacement. For example, this is a ball and there will be some normal force which is acting, and there will be one another force, let's say a weight, which is acting. Now in order to create a virtual displacement, we imagine that the ball is shifted upward and this displacement is given by delta y. Okay, so this is the virtual displacement, and then we need to identify the force which creating this virtual displacement. So here n is that force. So work done then is given by n del y. Just observe that again the virtual displacement is in the direction of n. So if it is, this is x and this is y direction, then the virtual displacement is in the y direction and n is also in the y direction. Therefore this n will create some work done because it's displaced in a same direction as given as similar to the n direction. So here I'm just revising the concept. So according to the virtual work principle, what happens? It states that virtual work done by external active force. So all the force which responsible for having the virtual work done, these are the active forces. So according to the virtual work principle, virtual work done by external force, external active force on an ideal system in equilibrium is 0 for all virtual displacement. So the principle states that the virtual work should be 0, and this virtual work is the consequences of this external active forces. So in the when we use the force and movement equilibrium equation in the previous tutorials, what what was the first step? That we need to draw the free body diagram, and we dismember each and individual members and use the free body diagram where we identify all the force and movements which are acting on the movement, which are acting on the member, sorry, and then we write the force and moment equilibrium equations. But here we need to consider the force which are the active forces. We don't need to consider the reaction forces or the internal forces. So we are not making the free body diagram here, but we are making the active force diagram, in which we have to show only the active forces, and active forces are those forces which are responsible for creating the virtual work. For example, here N is the active forces, mg is the active forces. So these two forces are there which actually responsible for some virtual work, and these two forces we need to take into account when we are using the virtual work principle. So according to this principle, the virtual work from all the active forces is 0 when the system is in equilibrium. It can be negative as well. So this is the concept of virtual work done. So we will solve few problems related to this concept, and then we will move to another concept where we will be solving the question by using the energy principle. So let's first solve few problems related to the virtual work principle first. So first let's consider a simple problem. So here we have given the L-shaped bar which is in equilibrium, and we need to determine the F. So first we need to uh, identify some virtual displacement which are going to happen due to these forces, due to these active forces. So this is my force F. This is 60 Newton, and here we have a movement which is 100 Newton meter. This is zero point 0.5 meter, and this is 0.5 meter, and this is 0.6 meter. Okay, then we assume some virtual displacement that due to these active forces the bar actually rotate, and it will rotate like this. So it will rotate here by angle del theta, and here it is del theta. So now we need to find this displacement. So this displacement will always be length multiplied by del theta, right? So the total length here is 0.5 plus 0.5 meter, which is 1 meter. So the length here is del theta, and in order to find this displacement, again it will be L del theta. So it will be zero point 0.6 del theta. So here it is just del theta. Here the displacement is del theta, and here the displacement is 0.6 del theta. Similarly, if you want to find the displacement here it will be L del theta, which is 0.5 del theta. Here we need to find the displacement because there is a force 60 Newton which is acting at that point. So we need to find the virtual displacement at that point. And you can also observe that all the displacement is in the direction of forces, which means all these forces and this movement actually will create a virtual work. And these are the forces we need to consider in the virtual work when we are writing down the virtual work equation. So our virtual work will be summation of all the virtual work will be 0 from the principal, and the work can be given as F 0.6 del theta This is 60 Newton force, and we have a virtual displacement of zero point 0.5 del theta here. So zero point 0.5 del theta, and the moment will create the work as well, which can be given as the moment multiplied by angular displacement. So angular displacement is already given, which is del theta here. So from the moment it will be 100 multiplied by del theta, and from the principle the summation of all these virtual work done should be 0. So we can take this del theta common. So we will get, so this is the equation we will get. So this should be minus, because you can see that here the displacement is opposite to the direction of forces. So here the displacement is from right to left and the force is from left to right. So the work done will be negative here. So this is negative work done. So we will have 0.6 F equals 130. So F will be 216.7 kilonewton. So this was a very simple example just to uh, understand the basic principle. So just to recap, here we have given the L-shaped bar and we need to calculate the this force, unknown force, and we use the virtual work principle here. And here what we did, first we assumed the virtual displacement. So we assumed the virtual displacement, we found out the displacement here, and we ensure all the forces which are responsible for the work done, and we call this active forces. So we identify these forces which are F, 60 Newton, and this movement M. Then we actually write down the equation of virtual work done, and according to the principle its summation should be equal to 0. Then on equating we can able to find the unknown force, which is 216.7 kilonewton. So you can see the principle is very easy to understand, and within very few steps we actually get the unknown force. And just also observe here, if you use the equilibrium equation, just a moment balance equation, you would have gotten this equation. So here we got this equation from writing the expression the virtual work. But if you do the moment balance analysis or you use the equilibrium method to find the force unknown forces, you would have get the same equation which is given here, right? So next let's move to the another problem. So here we need to determine the couple M which necessary for the mechanism to be in equilibrium. So the system is in equilibrium, and at the right hand side of the bar there is a distributed load which is acting. And in the previous class we actually show that how to convert a distributed load to a point load, and how to define the uh, location of that point load from the joint from the any of the joint. So let's first make a rough sketch of this problem. Okay, so at the end it is 600 Newton per meter. here it is 0.9 meter, this is 0.5 meter, this is 0.3 meter, and this is 0.4 meter. Then we assume some virtual displacement. So here we assume del theta, and here we assume del beta, right? So this displacement, this one is given as 0.4 del beta, and we are given the distributed load, so we need to convert it to a point load. And we saw in the last class how we do that. So it's a triangular load. So the magnitude of a point force, equivalent point force, will be given by its area. So it will be P half 600 multiplied by 0.9. So its equivalent point load will be 300 multiplied by 0.9. So it will be 270 Newton. And we also actually discussed that how to identify the distance from the punch joint. So for example, if my point load is acting here, equivalent point load, here it's P, the distance from the pin joint here is 2 by 3 L, and from the base of the triangle it is 1 by 3 L, right? So here we have a point load which is P, which is equal to 270 Newton, and this distance should be 2 by 3L, which is 2 by 3 multiplied by 0.9. So it will be 2 multiplied by 0.3, so it's 0.6 meter, right? And this remaining distance will be then 0.3 meter, and this is 0.6 meter. Okay, and we need to assign the virtual displacement at this point where the force is acting. So here the distance is L del theta, which is equal to 0.6 del theta, right? Similarly here the distance will be 0.3 del theta, right? And you can also figure out that this virtual displacement 0.3 del theta and this virtual displacement should be equal. So I can write 0.3 del theta equal to 0.4 del beta. Okay, so we will use this condition. So let's write the virtual work from these active forces, and there is a movement as well here, and we need to find this unknown movement. So the active forces are this P 270 Newton, which is creating the work done, and the another active member is this movement, which is responsible for the work done. So the work from the virtual work done principle, all the summation of virtual work should be 0, and the work done will be due to force 270 multiplied by displacement, which is 0.6 del theta, minus due to movement, and its angular virtual displacement will be del beta equal to 0, and we need to find the movement here. So movement will be 270.6 divided by del beta. Now we can use this equation, and according to this equation we have del theta by del beta equal to 0.4 by 0.3, and we can substitute this equation here in the expression. We will have m 270 multiplied by 0.6 multiplied by 0.4 divided by 0.3, and we need to solve this to calculate the value of m. So if you solve this, you will get m as 216 Newton meter. So this is the movement, unknown movement that you need to figure out. So just to recap here, we have given the system which is in equilibrium, and we have given the distributed load as well as the unknown movement, and we need to figure out the movement by using the virtual work principle. So first what we did, as in the last class, we have shown that first we convert the distributed force into a equivalent point load, and that we have done by calculating the area of the distributed load. Then we found the location of a centroid of that shape, and it is 2 by 3 from the joint. So we define the distance where this equivalent point load is acting. Then we figure out that this force, this equivalent point force, and this movement is responsible for creating the virtual displacement, and these are the active members. So we draw the free body diagram, we identify the active members, we identify the virtual displacement by these active members. And we also saw that we also observe one relation where I have shown in the green color, where the displacement in the green color, like zero point 0.4 delta B equal to the displacement here, which is 0.3 del theta. So both displacement are equal to each other that we have defined here. Then we write down the expression of work done due to these active members. And according to the principle, the summation of this virtual work done should be 0. And using the equation above and work done equation, we actually calculate the movement. So here we saw that we need to identify properly what are the virtual displacement, and also in some question we need to identify the relation between two virtual displacement, like we have did in this problem, where we find that the virtual displacement at one bar here is equal to the virtual displacement of this part of the bar. So it is very important to define the virtual displacement properly, and also if there is a relation between any of the virtual displacement that we have given or that we have defined, because it will simplify the problem and it will help you to calculate the magnitude of the virtual displacement, because once you get the virtual displacement, only then you can actually solve for the unknown quantities. So let's move to the next problem. So all these problems that we are solving, we need to follow the same concept. Only the thing is the complexity will be slowly increases. And here in these problems, the complexity is coming due to the way you are actually need to find the virtual displacement. So here in this problem, we have given a force P, which is 100 Newton, is applied to the lever arm of the toggle press. Determine the clamping force developed in the block when theta equals 45 degree. Neglect the weight of the block. So we have given the problem. So we need to determine the clamping force which is acting here. Let's say it's force Fe force, and since this, let's say this is my block which is given, and there is a normal force which are acting because it's in a contact with this part, so there will be a normal force as well. Now we need to assume the virtual displacement. So there is a force which is acting at point A. So let's say my virtual displacement looks like this. Okay. So due to this virtual displacement, let's say it's del theta. Here also this is del theta because it's the same angular displacement which is exerted due to this force P, and there is a displacement along force Fe. If I define the coordinate system x and y, then there is a virtual displacement in the y direction, which I can define yd, and there is a virtual displacement in the y direction along the force P, which is, let's say here it's ya. Okay, so until now we know that we need to define the virtual displacement because we need to use that in the virtual work expression, and then the summation of it is zero because the body is in equilibrium. And until now I have discussed that you need to carefully determine the virtual displacement. So we solved two problems and it was pretty easy to determine the virtual displacement because if it is a member, let's say this is my member and there is a virtual displacement del theta and this is the member of length L, then this virtual displacement can be given as L del theta. So we use the same principle in the above problems, but now we need to determine here del yd and del ya. Right? So you can see this distance is yd. So I can write yd as, and this distance, this is zero point 0.2 meter, right? So I can write yd as 2 multiplied by zero point 0.2 cos theta, right? And in order to find the del yd, this virtual small displacement, it is infinitesimal small displacement from yd. So if I differentiate this expression, I will get del yd equals minus zero point 0.4 sine theta del theta. Just when I take the differentiation of this expression, I will get minus zero point 0.4 sine theta del theta, right? Because I know yd can be given as 2 multiplied 0.2 cos theta, and on differentiation I will get del yd, which is zero point 0.4 sine theta del theta. For del ya, it's straightforward, which is L del theta, which is this distance is 0.5 meter, so it will be 0.5 del theta. So this is my del ya, which is straightforward. So now we identify the active forces, which are P and this Fe, because it's creating work done by creating a virtual displacement del ya and del yd. So these are the active forces. We don't need to consider other forces like reaction forces or internal forces. These are the only two active forces which are actually responsible for virtual work done. And now, according to the work done principle, the virtual work done by these two active forces will be minus P del ya minus Fe del y d equals 0. So both work done are 0 because the direction of force and direction of displacement are opposite to each other. And you can see here the direction of force P is in downward direction, but the virtual displacement is in the upward direction. We have assumed in the upward direction. And now we need to substitute the expression of del ya and del yd. So it's P, we have del ya, which is 0.5 del theta, and here we have Fe, and del yd, which is minus 0.4 sine theta del theta equal to 0. And just observe one another thing, that when we use the equilibrium method, force and moment equilibrium equations, then we need to consider the reaction forces and all. We need to identify all the forces which are acting on the system, and then we write down the equation for force and moment equilibrium. But here we need to consider only the active forces P and Fe. So there is another force which is acting in the horizontal direction or in the x direction, which is this normal force N. But it is not creating any work done. It's not creating any virtual work, because there is no virtual displacement in its direction, right? So here you don't need to consider all the forces, unlike when you use the equilibrium method. So just to recap, here the burden is actually due to the force P and Fe, because they are creating the virtual displacement. So these are the active forces, because these forces is actually creating the virtual displacement, and therefore these are responsible for the uh, virtual work done. So when you use the equilibrium method, you need to identify all the forces, right? But here you don't need to do that. You need to identify only active forces which are responsible for creating the virtual work done. So you don't need to consider this force N, because there's no virtual displacement associated with this force. So this is not an active force. Only active force is P and Fe. So these two forces we need to consider. So now when we simplify this, we will have P multiplied by zero point 0.5, and P we have given 100 newtons. So it is 100 multiplied by zero point 0.5 minus, become plus, Fe 0.4 sine theta del theta equal to 0. So you will have here minus 50, sorry, plus 0.4 Fe sine theta equal to 0. And again you can observe this, that if you use the equilibrium equation, you would have get the same equation, because this is force and this is force. So you would have got the same equation if you solve this problem by using the force equilibrium equation. So when you do the force balancing in the y direction, you will actually get this equation. Then you need to also do the force balancing in the x direction, which will relate this force, normal force, to horizontal reaction forces. But here you don't need to bother about this. So this is the equation you got, and the same equation you might have got when you do the force balance exercise and you balance the force in the vertical direction. So your Fe will be given as 50 by zero point 0.4 sine theta, and it says that when the angle is 45 degree, the system is in equilibrium, and we need to consider the force when the theta is in equilibrium. So it will be 50 by zero point 0.4 multiplied by sine 45. So we will get force which is 177.3 Newton. So this is the force we will get. So just to recap here, we need to use the virtual work principle to determine the unknown force Fe here. So it's a similar problem that we have solved, like we have solved in the previous one. Here we need to bother about the virtual displacement. Here the complication is actually arising from the virtual displacement, or from the way we are actually calculating the virtual displacement. So here we already know this YD, which is 0.2 cos theta twice, and there is a virtual displacement. There is a little change from this distance yd, and it is associated by del yd. So del yd is the virtual displacement which is caused by force Fe, unknown force Fe. So if I have the equation yd, I can differentiate this equation in theta to get the equation for del yd, because it's infinitesimally small distance. So I can write down del yd as zero point 0.4 sine theta del theta, which is I got when I differentiate yd with respect to theta. Now I need to identify another virtual displacement del YA, and it is straightforward. I use the relation L del theta, and from there I got zero point 0.5 del theta, which is the virtual displacement del YA, right? So once you figure out the virtual displacements, it's pretty much easy. Now we use the virtual work principle, where the summation of all virtual work will be zero, and we identify the virtual work done by these active forces P and Fe, and we equate it to 0, and then from there we actually got the unknown force Fe. So in the virtual work problem, the complication arises when you actually find the virtual displacement. Otherwise you have to follow the same concept in every problem. So let's solve the last problem related to the virtual work, then we will move to the energy principle. So again we need to follow the same concept in this problem, only the thing is, as usual, we need to find the virtual work, we need to find the virtual displacement. Okay, so that's the only tricky part, because you need to use, sometimes you need to use very heavy mathematical algebra to find the virtual displacement here. Otherwise the concept will be the same. So here we have given the bar AC, which is connected to bar BD by a pin that fits in the smooth vertical slot. The masses of the bars are negligible if the moment at A is 30 Newton meter. What is the moment at B, which is necessary for the system to be in equilibrium? So we have given the moment at point A, and we need to find the couple or the moment at uh, point B, right? So as usual, we will make active force body diagram. So here we have not given any forces, but we have given the movement. So this movement will responsible for the virtual work done. And then there is the virtual displacement. Here there is a virtual displacement of this BD bar as well. It will move to here, right? So this is the angular displacement of del theta, and this is del beta. And let's say this is my del y, and this is my del x, and this is my del y, right? And you need to find this virtual displacement, here. You already know this, which is del y, and this is del x. So you can see that problem is little much more involved, because it's mathematically or algebraically little more involved when we try to find the virtual displacement. Otherwise, the concept is similar. So let's find this distance L first. So if let me make the coordinates. So this is my x and this is my y. So this can be given by Pythagoras theorem and it can be evaluated by Pythagoras theorem. So x here is zero point 0.7 and y here is 0.4. So we can easily find this L, and which is given as x square plus y square equals L square. So it's zero point 0.7 square plus 0.4 square equal L square, which is so here L is 0.806 meter. So from this equation, if I differentiate this equation, because I need to find out the delta x and delta y here, right? So like a previous question where we differentiate the yd expression to get del yd. Similarly here, if I differentiate this equation, I will get 2 del x plus 2 del y equal to 0. So from this equation I can write, sorry, I will have 2x dx plus 2y dy equals 0, and from this equation I will have x dx equals minus y dy. So dx is del x and dy is minus del y because it's going down. So you can see that earlier this is our actual distance from the pin joint y, but now it's going down. It's going toward in the negative y direction. So it's dy, the change in y is negative. It's minus del y. So if I substitute in this equation, I will get x del x equals y del y. So I will have del y equals x by y del x. We already know x and y, which is 0.7 and 0.4. So it's 0.7 by 0.4 delta x. So this is the expression of del y. So this virtual displacement is del x, right? And del x can be given as L del beta, and the length here is y. So it's y del beta. Okay. So here I can write del beta as del x by y. Right? I am writing del beta because when you have force, the virtual displacement can be given as L del theta, right? But here you have given the movement. So the movement will create virtual angular displacement, and del beta and del theta is my angular displacement. So I'm writing in terms of del beta, not in terms of L del beta, which is required if the force is given. So similarly, this displacement, this one, which I am marking here, this is L del theta. L del theta, and this can be given as, so you can see that this side is del y and this side is del x. So this can be obtained, L del theta can be obtained by Pythagoras theorem as well, which is equal to del x square del y square. So again, since the moment is given, this is for the moment there will be an angular virtual displacement, not the virtual displacement, not virtual translation displacement. There will be a virtual angular displacement. So I will write in terms of del theta, which is del x square plus a del y square divided by L. So I have identified del theta, which is the angular displacement caused due to movement ma, and this is my del beta, which is caused due to this moment mb, unknown moment mb. So you can see that these two moments are the active component, and we need to identify the active component, and these two moments are the active components. So these two moments will create the virtual displacement, virtual angular displacement, which is responsible for the virtual work done. So my expression for the virtual, so I can still simplify this expression here. So I can write this as 1 by L 1 plus del y by del x square del x. So just mathematical simplification. So this is my del theta. So now my summation of all virtual work should be 0 for the system to be remain in equilibrium. So it will be m a del theta minus mb del beta equal to 0. Now I need to substitute the angular displacement here, del beta and del theta. ma equals ma multiply 1 by L 1 plus del y divided by del x mb multiply del beta we found is del x divided by y. So if I take the common and put out del x, so in earlier example we actually took the common and put del theta out of the, and we got the force balance equation. Here we doing the same thing with del x equal to 0, and we got this moment equation, which definitely you will get if you do the moment balance analysis, right? So if you simplify this, you will have ma divided by L. Here you have del y plus del x square plus del x square. You can, and this is mb by y equals 0. You can see this term in the blue color is actually L square. Okay, so if L square under root will be L, so this L and this will be cancelled. And when you simplify, you will get mb equals to ma, which is 30 Newton meter. So in this example as well, you saw that we have used a similar concept, but it become mathematically more involved to find the virtual displacement. So here the moment is causing the angular displacement, which are virtual, and it responsible for virtual work done. And all the tricks and algebra went to calculate these virtual displacement. So the complication may arise in the question, and in most of the time, these complications are due to finding the virtual displacements. Once you identify the virtual displacement, it's a straightforward problem where you actually write down the work done equation and you find the unknown force or movements. So here the unknown moment mb is 30 Newton meter. So now let's talk about the energy principle. So in the case of the spring system, what happened? The work done is actually the stored potential energy of the spring system. Similarly, for the conservative forces like the gravity, the work done is actually the stored potential energy of that body, which is falling in the presence of the gravitational field, or which is moving in the presence of the gravitational field. So the potential energy of the spring can be given written as f dx, which I'm integrating from 0 to x, and if force of spring is kx, then the potential energy will be 1 by 2 kx square. So this is my potential energy of the spring. Now, if you have given the spring system or any elastic member, or the member which has given the weight, then the work done principle is virtual work in equilibrium is equal change in total elastic potential, elastic and gravitational potential energies for all virtual displacement. So until now we have seen the principle of work done, virtual work done, which is equals to 0 if the body is in equilibrium. But here if you have given the elastic member which have a weight, or the member which have a weight, then the virtual work in an equilibrium condition equal to the change in the total elastic and gravitational potential energy. And the work done in these members can be given as stored potential energy. For example, work done in the spring can be written in terms of a stored potential energy of the spring, which is half kx square. Similarly, the work done in the falling body, which has a weight, can be written as the stored potential energy due to the gravitational force. So the work done principle is the virtual work, change in the virtual work, minus change in the potential energy due to elastic member and due to gravitational force equals to 0. So the virtual work done states that virtual work principle states that the virtual work will be equal to change in the elastic and gravitational potential energy. So this is the work done by all the active forces except elastic and gravitational forces. And let's say you have uh, not given any non-potential forces, or the forces you have given it's completely due to the elastic member or the weight, then you can write, so this component will be 0, then you can write change in the elastic member plus gravitational potential energy equals to the total change in the potential energy, which is equal to 0, because this left hand side will be the 0. And you can write this term as for single degree of freedom dV by dx equal to 0. So if the system is in equilibrium, then the derivative of the potential energy with respect to x in a single degree of freedom should be equal to 0, or there is no change in the potential energy when the system is in equilibrium. So here I am just revising the concept to solve the problem using this principle. Similarly, you can actually identify whether the system is in stable condition or in an unstable condition. So for the stable condition, the double derivative of the potential energy should be positive, and for unstable condition it should be less than 0 or should be negative. And if it is 0, then it should be neutral. So in the various books you might have seen, maybe it actually explained in a very nice manner that you have a curved space and there's a ball. So the stability means that if you provide some perturbation to this ball, the ball will move, but when these perturbations are removed, the ball will come back to its original place because the system is in equilibrium. Similarly, if you have a surface like this and you give some perturbation in any of the direction, the ball will completely displace from its original position and it will not come back to its original position, and this system is unstable. And for a neutral condition, what happens that you have a ball which is in the flat plate surface, and if you provide the perturbation it will move, but once you remove all the perturbation the ball will become unstable again. So it become unstable, but the instability is not dominant once you remove the perturbation. Okay, it becomes stable again. So this is a neutral condition. So this is very nice way to explain the instability or the instability in the problem. So now we will using this principle where the change in potential energy is zero when the body is in equilibrium. So we will use this principle to calculate the unknown force and movements. So let's start with an easy problem. So here we have given if the potential energy for a conservative 1 degree of freedom system is expressed by the relation V, which is 24 sine theta plus 10 cos theta, where theta lies from 0 to 90 degree. Determine the equilibrium position and investigate the stability at each position. So we have given the potential of a system which is 24 sine theta plus 10 cos 2 theta. Now we need to determine the equilibrium position. So we have just discussed now that for the equilibrium the change in the potential energy should be 0. So here the potential energy is given in terms of theta because that's the only degree of freedom we have given. So it is dy by d theta should be equal to 0. So now we have to differentiate this equation. So we will have dv by d theta. So when we differentiate, we will get 24 cos theta minus 20 sin 2 theta. Now if the system is in equilibrium, then dv by d theta should be equal to 0, which means this expression should be equal to 0. So 24 cos theta minus 20 sin 2 theta should be equal to 0. In order to find the equilibrium position theta, we have 24 cos theta, and this expression we can expand. We can write down as 20 multiplied to sin theta cos theta equal to 0. So we have used the trigonometric identity where sin 2 theta equals 2 sin theta cos theta. Then we take cos theta common, so it will be 24 minus 40 sin theta equal to 0. So we get two sets of equation here. We can write like cos theta equals 0, and we can also write 24 minus 40 sin theta equals 0, and 24 equals 40 sin theta. So here we have 24 by 40 equals sin theta. So here theta is sine inverse 24 by 40. So we will get theta as 36.86 degrees. And from here we will have theta equals cos inverse 0, which is 90. So we will have theta 36.86 from here, and from above this expression we will have theta equals 90 degree. So these are the two equilibrium position we get where the system remains in an equilibrium. So this for when the theta is 36.8 or 90, the system is in equilibrium. Now we need to find out whether these positions are stable or unstable. So for that we need to calculate the double derivative of the potential, and we need to check its sign. Just we have just discussed that if it is positive then it corresponds to stable system, and if it is negative then it's indicate unstable system. So the double derivative will be so it is minus 24 sine theta, and it is minus 40 cos 2 theta. Sorry. Yes. So minus 40 cos 2 theta minus 24 sine theta. So you need to determine whether the system is in equilibrium or not at this fixed position. So for theta equals 90, we have minus 4 cos 2 multiply 90 minus 24 sine 90. So cos 180 will be minus 1, so it is 40, and sine 90 is 1, which is minus 24. So it is 16, and you can see it is greater than 0. So at theta equals 90, the system is in stable condition because its double derivative is 16, which is greater than 0. Now we need to check the another equilibrium state. Theta equals 36.86. So here we have 40 cos 2 multiply 36.86 minus 24 sine 36.86. So this is minus 11.213 and this is minus 14.39. So you already know that the answer will come in the negative, and it will be roughly equal to minus 26, which is obviously less than 0, and the system is in unstable condition at theta 36.86. So just to recap here, we have given the potential energy of the system V, which is given in terms of theta, and we need to find the equilibrium position and investigate the stability on these equilibrium positions. So we just discussed that For the system to be remain in equilibrium, the change in potential energy should be equal to 0 here, which means that here the dV by dt should be d theta should be equal to 0. So using this relation, we found out the equilibrium position, which is theta equals 90 degree and theta equals 36.8. Now we need to check the instability of the system. So for that we need to find the double derivative of the potential energy with respect to theta, and we found that the equilibrium state when the theta equals 90 is stable because the value of this double derivative is positive, so it's a stable condition. And another equilibrium state, theta 36.86, is unstable because its double derivative come out to be a negative, which is less than 0, and hence it's unstable condition. So these are my equilibrium position of the system. One is stable and one is unstable. So let's solve next problem. So now this problem we will be using the we will be using the energy principle, but we will solve this same problem by using the virtual work principle as well, which we used in the last few problems where we defined the virtual displacement and we found the virtual work done, and according to the virtual work principle, the summation of all virtual work should be equal to 0. So this problem we will be solved by two methods. First, we just recently discussed or revised the method of using the potential energy, where the change in potential energy should be equal to 0 when the system in the equilibrium position. So we will be using this method to solve this problem. Then we will use the virtual work principle to solve this same problem, and we will find that both will give the same answer. So you can use any of the method to solve this problem or any problem. So just uh, make a schematic diagram of this problem. So this is angle theta, this is angle theta, and this is 0.25 meter, this is 0.25 meter, and there is a spring force here. So this distance, so in the question we have given that we have a 5 kg uniform serving table is supported on each side by pairs of two identical links AB and CD and spring CE. If the bowl has a mass of 1 kg, determine the angle theta where the table is in equilibrium. We have given the stiffness 200 Newton per meter, and which is unstretched when theta equals 90. So we have given the mass of the table and the distance, this distance is YGT, and this one is again the same YGT, and this distance is, let's say, B. It's a distance between this centroid of this bowl to this table. So this is my B, and this is YGT, and this is also YGT, and we need to consider this distance as well. I mean, if you zoom this figure, you will have, this is your table and this is the centroid of the table from where the mass of the centroid is of this table is acting. So this distance is A, and the remaining one is YGT. So from centroid, table centroid, the distance is a plus ygt. Or okay, so from table center, the distance is ygt plus a, and from this bowl center, the distance is ygt plus b. And ygt is actually this 0.25 sine theta. Okay, so now there is a spring system and there is a weight which is acting, and we saw that the potential energy due to the weight and the spring system will define in terms of a work done due to spring and due to the weight, and it's equal to its virtual work done should be equal to zero, or the change in the potential in the elastic member plus due to the gravitational force should be equal to zero. There is no other force acting which may be considered as an active force, right? So just we have discussed or we have revised, the virtual work principle should be given as the change in elastic and potential gravitational potential energy. So there is no, so we have given the force in terms of, we have given the spring force and we have given the weight. So there will be a potential energy related to the weight which will be captured by this, and there will be a change in potential energy due to the spring. There we have not given any force, we have not given any active force which can produce virtual displacement. So this term is zero, and we saw that change in the potential energy due to elastic member and due to gravitational force equal to it's a total potential energy, and the total potential energy should be equal to change in total potential energy should be equal to zero when the system is in equilibrium, right? So the potential energy due to the gravity is mgy mg gt y bar gt plus y bar gv. So we have, or I should write, because we have a different mass system we have given here. The mass of the bowl is 1 kg and table is 5 kg, so I should write this as mbg by gb bar plus mtg y bar tv. So this is my total potential energy due to the gravitational field. So mb is 1 kg, so it's 9.181 multiplied by 0.25, sorry, this is my sine theta plus b, and mass of the table is 5 kg multiplied by 9.81 0.25 sine theta plus a. So we will get 7.357 sine theta plus 24.52a plus 4.9b. Similarly, you can write down the potential energy due to the elastic member here, because it should be the summation of potential energy from elastic member and from the gravitational field. We already write down the potential energy from the gravitational field. Now from the elastic member, for the elastic member we have given the spring and it will extend in the x direction. So if this is my x and this is my y, it will be extending in the x direction, and that will be given as 0.25 cos theta, right? Because if this is my 0.25 sin theta, then the extension of spring will be 0.25 cos theta. So it is, stiffness is 200 Newton per meter multiplied by 0.25 cos theta whole square. So when you solve this, you will have 6.25 cos square theta. So the summation of, so we know that for the system to be in equilibrium, the summation of potential energy due to the gravitational force and the elastic member should be equal to 0. So the summation of the potential energy will be 6.25 cos square theta plus gravitational potential energy, which we found 7.357 sin theta plus 24.52a plus 4.9b. So this is my total potential energy. Now change in total potential energy should be equal to 0. So this change I can write as dV by d theta should be equal to 0. So if I differentiate the above expression, I will get minus 12.5 cos theta sin theta plus 7.357 cos theta minus 12.5 . Yeah, that's it. So this should be equal to 0. So I can simplify it as cos theta, I will take common, minus 12.5 sin theta plus 7.35 equal to 0. So here I will get cos theta equal to 0 and 12.5 sin theta equals minus 7.35. So sin theta equals 7.35 divided by 12.5. So theta will be sin inverse .588. So theta will be 36.1, and we have also cos theta equals 0. So from here we will get theta equals 90 degree. So these are the equilibrium theta we need to find out. So here to find the equilibrium theta, we use the potential energy concept. So just to recap here, we first identify the active force and the potential energy and the spring potential energy, or if there is a work done due to the active force. So there are no active force which create, there are no other active force apart from the weight as well as the spring force which will create the work done. So we use the principle that the active force which are non-potential in nature, its work done is equal to the change in the potential energy due to the elastic member as well as the gravitational member. So if there is no force other than the gravity or the weight and the elastic or the spring force, then the change in the potential energy is defined as the summation of change of the potential energy from elastic member and gravitational force. And for the system to be remain in equilibrium, this total rate of change of potential energy should be zero. And following this concept, we first identify the potential energy from mass and then potential energy from the elastic member, which is spring here, and we write down the expression for total potential energy. Then we use the fact that the derivative of this potential energy with respect to the theta should be zero for the system to be remain in equilibrium. We use this concept to find the unknown equilibrium position. Now we will solve the same problem by using the virtual work principle. So there we have already solved 4 questions related to that principle. So there we don't need to distinguish between the force which is causing the weight or the force which is causing the work done due to the elastic member, which can be written as the elastic potential energy. We will actually accumulate all the active forces together. So here we solve the problem by using the energy method. So just to recap again the energy method. So according to the energy method, the work done from the non-potential forces, virtual work done from the non-potential forces should be equal to the change in potential energy due to the elastic member as well as the gravitational force, right? So this is my virtual work done due to non-equipotential forces, and this virtual work done should be equal to change in potential energy due to gravitational force and the elastic member. In this problem, since we have given only the weight as well as the spring force, which means there are no non-potential forces. So the contribution from the left hand side should be zero, and we can write potential energy from gravity plus potential energy from the spring as the total potential energy. Now the change in this total potential energy should be equal to zero for the system to be remain in equilibrium. So here what we did, we found out the potential energy from the gravity and then from the elastic member, and then we uh, eq- we equate its change. Then we actually find out the change of this potential energy with respect to theta and equate it to zero. We now solve the same problem by using the virtual work principle. So in the virtual work principle, we don't need to identify the non-potential force and the potential force. So all the forces we will club together, and we will actually looking for the virtual displacement by these forces. Okay. So according to the virtual work principle, the virtual work done from all the active forces should be equal to zero. So here I am actually containing all the active forces. This could be due to weight also, and this could be due to elastic member as well. So it contains all the active member from weight, elastic member, from other external forces, which will create the virtual displacement. In the above, when we use the energy principle, this actually contain only active forces but without weight and without elastic member or the spring forces. So that actually equals to the change in potential energy due to weight and elastic force. But in the virtual work principle, the summation of all the virtual work done should be equal to zero, and the force which create this virtual work done contain all the active forces in terms of weight, elastic, and everything. So now we solve this problem by virtual work principle. So we have hello, hello. You have any doubt? So as of now, we use the energy principle. Now we use the virtual work problem, or sorry, virtual work method to solve the same problem. So first we need to identify the assumed displacement. Okay, so this is my rough schematic, and first we need to identify the active forces. So earlier we don't need to identify the active forces because there were no non-potential forces were there. So we need to consider only the potential energy due to weight and elastic member, and we have already given here. But now we need to consider all the active forces. So this is my assumed. So my assumed displacement can be given by this blue color. So earlier the distance was ygt, but now there is a virtual displacement in the y direction, which is del y gb. So this is gb, and here there is a virtual displacement del y bar gt, and there is a virtual displacement in the x direction also, which is del c, which is okay. So there is a weight here due to table, and there is a weight of this bowl. And we see that all these three forces are the active forces because this spring actually causing this virtual displacement del xc. This weight is actually causing virtual displacement del yat, and this weight due to bowl, the weight of the bowl is actually causing the virtual displacement in the same direction, which is del ygb, right? And I said in the when solving the previous problem that I actually said that the only tricky part in the virtual work is to calculate the virtual displacement because it's the only part which is mathematically involved. So the first we will actually identify the virtual displacement. So we know that we already found the y del gb, which is 0.25 sine theta. So this is my 0.25 sine theta, and this remaining distance, this one, is plus b. So it is 0.25 sine theta plus b. And you can see when you apply the force, there will be some virtual displacement. So there is an increment from this y del gb by del y gb. Okay, so when you differentiate this expression with respect to theta, you will get del y gb, which is 0.25 cos theta del theta. So this is the virtual displacement. Similarly, y del gt is 0.25 sine theta plus a. So plus a, just to be again repeating here. So let's, if you zoom out this portion of table, so this is your table, this is the centroid of the table. So this is your distance a, and this is your distance 0.25. Sorry, this is sine theta. Oh, this is cos only. Yeah, this is your 0.25 sine theta. This distance from this datum. So the distance is 0.25 sine theta plus a. This is the centroid of table from which mass is acting, plus a. So if you differentiate this, because there is an infinitesimal change by del y gt, which is the virtual displacement here. So it will be 0.25 cos theta del theta, and xc is 0.25 cos theta. So change in xc will be minus 0.25 sin theta del theta. So here we identify all the virtual displacement. So now, according to the virtual work principle, the summation of all the virtual work should be equal to 0. So here we have yb delta y bar gb minus yt delta y bar gt minus fs delta x equal to 0. So here you have 0.905, 0.25 cos theta minus 24.525, 0.25 cos theta minus 50 minus 0.25 sin theta, which is xc. So here I took the common for del theta equal to 0. So when you solve this, you will get theta equals 36.1 degree and theta equals 90 degree. So it's the same answer we got when we use the energy principle. So just to recap here, this question we have solved by two principal methods. First we use the energy principle where we define the potential energy from gravity and elastic member, and to system remain in equilibrium, the change in the total potential energy should be equal to 0, and this condition, when we apply this condition, we actually got the equilibrium angle. Then we actually apply the virtual work done principle where the virtual work done from all the active forces should be equal to 0. We identify all the virtual displacement, we identify all the active forces which are acting here, and using the principle of virtual work done, we equate the equilibrium position, and both give the same answer. So let's move to the next question. So this question is very much similar to the previous one we just have solved. So here you can also use the energy principle to solve. So you can solve this question, you can practice this question. The concept is very much similar that we have just saw. You can move to the next one here because it's a bit different question. So you can understand solving this question. So here we have given the uniform block having a mass m rest on the top surface of the half cylinder. We have to show that this is a condition, the condition which we have shown in the second figure. We have to prove that this condition is the unstable equilibrium if h is greater than 2r. So h is the height of this block, and if it is value of this is greater than 2r, then this position is unstable position, right? So as you can identify, there is no elastic member, there is only a gravitational force. So when we use the energy principle, we need to concern about only about the potential energy due to the gravity, because the potential energy due to the elastic member is 0, because we assume that these blocks are rigid, they are not elastic in nature and they are not non-rigid. So this is potential energy due to elastic member is 0, and the total potential energy then equal to the potential energy due to the gravity, and the potential energy due to the gravity is mgy, and now we need to identify y. So you can see that y is given as r plus h by 2 cos theta plus r theta sin theta. So this is my y. So y is r plus h by 2 cos theta plus r theta sin theta. So my potential energy will be mg r plus h by 2 cos theta plus r theta sin theta, and this is my total potential as well. And for the system to be remain in equilibrium, the change in the total potential energy should be 0. So its derivative will be minus RH by 2 sin theta. Here we have R sin theta plus minus, no, plus R theta cos theta. So for system to be remain in equilibrium, this whole equation should be equal to 0. So we will have plus r sin theta plus r theta cos theta equal to 0. So here we have minus r sin theta, here we have r sin theta. So we will have h by 2 minus h by 2 sin theta plus r theta cos theta equal to 0. So this condition is satisfied when theta is 0. Because when you plug theta equals 0, this whole equation will become 0. So one of the solution is theta equal 0. So this is one of the equilibrium position. So now we need to check this criteria. So in the question we need to prove that the system is in unstable equilibrium. So to find the instability, we need to calculate the double derivative of the potential and check this sign. So we need to prove the system is unstable. So we need to prove that the double derivative of potential should be less than 0. And this will happen when h is greater than 2r, we have given here. So the double derivative will be minus h by 2 cos theta plus r cos theta minus r theta sin theta. So to find the instability at a point, equilibrium point, we have already found the equilibrium point. We show that at theta equals 0, LHS will be 0. Right? Because this sin theta will be 0 and theta will multiply cos theta will also 0, because cos 0 will be 1 and theta is 0, so it will be 0 as well. So we will have here minus h by 2 plus r. So this is the condition we will get, minus h by 2 plus r mg. So this system is positive when this is greater than this. When r is greater than h by 2, then this quantity will be positive. So the positive double derivative equivalent to the stable condition. Similarly, this quantity is unstable when this negative quantity is greater, which means minus h by 2, or this h by 2 magnitude should be greater than r. So then this whole quantity is less than 0, it should be negative, and then the system is unstable. So for unstable system, h by 2 should be greater than r, or we can write also like h should be greater than 2r to the system to be remain unstable, right? So in this question we just need to figure out whether the system is unstable or not, or what are the conditions for the instability for this unstable condition. So we use the energy principle. We first find out the potential energy. We then use the principle that the rate of change of potential energy should be equal to 0. So when we use that, we actually got the equilibrium position theta, which is 0. Then we found the instability by taking the double derivative of the potential energy at the equilibrium position. So at equilibrium position, we got the relation minus h by 2 plus r and some constant mg. So we saw that if this positive quantity r is greater than h by 2, then the system is stable because the whole quantity will be positive. And if this quantity is negative quantity is greater than r, then this whole quantity is negative, which means the system is unstable. And this is exactly the thing we need to prove. And there is a similar question here. So here we are given the pin bar are held in a place by a linear spring. Each bar has weight W and length L. The spring is unstretched when alpha is 90 degree. Determine the value of alpha in the range 0 to 90 for which the system is in equilibrium. So for the system to be remain in equilibrium, we know that the total potential energy should be equal to 0. Total change in the potential energy should be equal to the 0. And in the system, we have given the elastic member and we have given the weight of this bar, which means the total potential energy should be the summation of potential energy from elastic member, which is spring, and the weight. So the potential energy will be given as Vg plus Ve, and the total gravitational potential energy is given by W L by 2 sine alpha. 2 because there are two bars, both have a weight, and this L by 2 is the vertical distance, L by 2 sine alpha, plus potential energy due to the spring, which is kx square, and x is this distance, right? This distance is x, which is 2L cos alpha. So it is 2L cos alpha whole square. This is x. And we know that the potential energy of the spring is half kx square. So x is 2L cos alpha. So if I take the derivative and equate it to 0, the system should be remain in equilibrium. So the derivative will be WL cos alpha minus 4KL square cos alpha sin alpha should be equal to 0. If I take cos alpha common, then I will have WL minus 4KL square sin alpha equal to 0. So alpha is 90 because cos alpha is 0. So from this condition I will have alpha equals 90 degree, which is the equilibrium condition, and we have already given in the question that at the equilibrium condition the spring is unstretched. And from this we have WL minus 4KL square sin alpha equal to 0. So WL equals 4KL square sin alpha. So sin alpha is W 4KL. So my alpha is sine inverse W divided by 4KL. So this is my another equilibrium angle. Now in order to find whether this equilibrium angle is stable or not, we need to take the double derivative of the potential, which is minus WL sine alpha plus 8KL square sine square alpha minus 4KL square. And when we substitute alpha as sine inverse W by 4KL, I will have minus WL, and instead of sine alpha we will have W by 4KL, right, from here, plus 8KL square multiplied by W by 4KL whole square minus 4KL square. And if you solve this, we will get W square by 4K minus 4K L square. So when W is greater than 4KL, we will have a positive quantity and the system is stable, right? And we have given the equilibrium angle, which is sine inverse W by 4KL. And here the equilibrium angle to be valid, since it is given sine inverse plus some quantity, this quantity should be this quantity should be less than 1, because only then you will have a real value of equilibrium angle. So W should be less than 4KL, right? So for this condition, when the W is greater than 4KL, this quantity is positive, which is correspond to the stable condition. But we can see that from this equilibrium condition that sine inverse x, you will only get the real value of this quantity when x is less than 1, which means this quantity W by 4KL should be less than 1, which means that W should be less than 4KL. And when W is less than 4KL, this condition, this quantity is negative, which means that for this condition, the system is unstable. So when you have given the expression and you need to verify whether the system is stable or not, first to look at the expression and define the conditions that for what W, for what expression of W or KL, you will have a stable or unstable system. You can also look the equilibrium expression and check out when it is valid, because we have already obtained the equilibrium location, and that location is real. We can define that location by expression W by 4KL, and from the equilibrium position we saw that only condition is allowed when the W is less than 4KL, because only then this sine inverse quantity will give you a real answer. And for this condition, when the W is less than 4KL, the system is unstable, because then this quantity double derivative is less than 0, it's a negative, and hence on a negative one the system is unstable. So that's it for today. There's still one problem left, which this one, and we have already solved the problem previously, and you can use the same concept exactly to solve this problem. So in this tutorial we looked the problems related to the virtual work, and we have also used the energy principle. So in half of the problem we use the virtual work principle, and in the remaining half we use the energy principle. We learned how to obtain the unknown forces using virtual work concept, and we also solve problem related to the potential energy concept, where we say that the change in potential energy should be equal to 0, and we identify the fixed point by using that concept, and we also identify whether that fixed point is stable or not by calculating the double derivative of the potential energy and checking its sign. And for each problem, we started with a very simple problem in both the cases, for virtual work and for the energy principle. We started with very simple problem, and eventually we moved to the tougher one. So in all the problem, the concept remained the same. The concept will be either virtual work principle or either the energy principle. So we solve the problem by two concepts. So the concept will be either of these, but the complexity usually arises in the mathematical algebra. So for example, in the virtual work problem, we saw that it's sometimes a bit lengthy, or sometimes the algebra is more involved when we calculate the virtual displacement. Other than that, the concept is same in all the problem related to the virtual work. So that's it for today. Thank you.